Hi everyone, I'm Jose Algarin, Program Specialist for the Climate Variability and Predictability Program, CVP, at NOAA's Climate Program Office. Thank you for joining us for the sixth session of the webinar series called Decadal Climate Variability and Predictability Studies. This is a continuation of a series of webinars for the climate program, for the CVP program that started several years ago. Today's webinar is recorded and it will be available at the CVP under the Webinars tab. If you missed any of the prior CVP webinars, I encourage you to view them from our website. CVP supports research, our process understanding of the climate system through analysis and field studies. This webinar series covers the 10 projects funded by CVP on the topic of decadal climate variability and predictability, all of which started in September 2020. The call for these studies was CVP's contribution to the national and international research interest in this topic. The main goal of these studies is to identify the state, mechanisms, and sources of climate predictability on the interannual to decadal timescale. This research will lead to future improvements in skillful decadal prediction systems for climate, ocean, and atmosphere. In this series of webinars, researchers will share the latest results from these projects and will allow them to discuss the importance of their work, outcomes, and lessons learned with a broader scientific. We hope that you enjoy today's talks and ask questions. Speaking of questions, if you have one for 1 hour questions, speaking of 1 hour presenters, please use the raise your hand feature, which you can find on the control panel for GoToWebinar. At the end of the presentation, I will only use those who have raised their hands so that they can questions using their audio. You also need to unmute yourself after you do so. If you have audio problems, I will ask you to type your questions in the questions box, which can also be found on the control panel. Now let's get to the presentations. Our first speaker today is Dr. Timothy Del Sol. He's a professor at the Department of Atmospheric, Oceanic, and Earth Sciences at George Mason University in Fairfax, Virginia, and a senior research scientist at the Center for Ocean and Land Atmosphere Studies at the same institution. Dr. Sol's research explored which feature climate-shifted timescales from weeks to years. Dr. Del Sol, thank you so much for joining us. At this time, we'll turn over the controls to you.
Can you see the first slide? So I didn't hear an answer. Can everyone see the first slide?
Yes, we can.
Okay, great, thanks. Okay, so thank you for this opportunity to discuss this work. The work I'm going to discuss is...
Yes, we can.
Okay. The question I'm going to address here is whether models correctly simulate Atlantic variability. This is work I've been doing in collaboration with Michael Tippett. Just to orient you about the problem that I'm discussing, here I'm showing A and B indices from observations, that's the black, and from 2 model simulations, those are in color. These time series, I'm only showing the anomalies, but I've shifted the curves just so it's easier to compare them. And the basic question is, do the models simulate the variability in a way that's consistent with observations? Now, the way these models are run, these are just simulations, so there's no correlation between the model series and the observation series. And so the basic question we're asking is, are the statistics of the simulation consistent with the statistics of observations? And a distinctive feature of these time series is that they're serially correlated, and that can be quantified by the autocorrelation function. So the question we're having here is, are the autocorrelation functions the same between models and observations, or equivalently, is the power spectra the same between models and observations? So that raises the question, how do you compare the autocorrelation functions, or how do you compare power spectra? So there's a very nice paper by Robert Lund, which I highly recommend, which has addressed this question. And in there, he notes a few features of the available techniques. And one is, if you take the available tests for comparing power spectra, they tend to have low statistical power, which means that you need pretty large differences in spectra in order to detect a difference. And a second point which we discovered, which is if you take the available autocovariance tests, they're just not sufficiently developed. And what I mean by that is there are certain quantities that should be positive definite, and they're not. And so when they're not, you can't apply the test. And so it becomes a problem applying it, so they're not very reliable. So I've been working with Michael Tippett and others on developing a method for comparing serially correlated time series. And the basic idea is this: we assume the data is generated by what's called a vector autoregressive model of order P. And what that is it takes the current state and represent as a linear combination of previous states plus noise, where these A matrices are constant, and then this noise term is Gaussian white noise with a covariance matrix Q. So this is a method that I've been working on for quite a while, but you may not be familiar with this kind of model, but you may be familiar with what's called a linear inverse model, which is really a stochastic model of this form. And it turns out that if you sample the output of a linear inverse model at discrete intervals, then it's indistinguishable from a vector autoregressive model of order 1, which means that a linear inverse model is just a special case of the model I'm considering. And the linear inverse model has been used in a wide range of studies, and I've listed a few papers here. In particular, it's been used in the North Atlantic, and that's the focus of my talk here. So I've also been working on this for quite a while. I've published a number of papers on this. The last paper we published was to generalize this method to include annual cycles, but that method only looked at univariate time series. That means you're just looking at one time series at a time and comparing it to one other time series. And so the material I'm going to talk about today is extending that to multivariate annual cycles. So the general idea is we're going to start from the vector autoregressive model, but we're going to add in periodic signals. So these could be annual cycles or diurnal cycles, and there will be extra coefficients, which I've labeled here as C, that will need to be estimated when we include that. And so the idea is that we assume the data is generated by a model of this form, and that generates a sample, which I've labeled here Y1 through Yn. And then we have another stochastic model of the same form. It generates output, and we assume the Y star is output from that. And then the question is, did these two time series come from the same stochastic model? And that's equivalent to asking, if we assume that they came from a model of this form, are the coefficients of the first model equal to the coefficients of the second model? And so that means, is this A1 equal to this A1 star? Is this AP equal to AP star, and C equal to C star, and so forth? So it turns out that you can derive a test for this hypothesis. You can use something called the likelihood ratio test, and it ends up giving you a statistic that's of this form, where the Q hats are the best estimates of your noise covariance matrix separately, and then under the null hypothesis, you estimate it that way. And then we get the statistic, which I'm going to call the deviance in the rest of my talk. So the deviance is a measure of how dissimilar the two models are. So for instance, if all the coefficients are equal, the deviance becomes 0. And if there's any difference between the parameters, then the deviance is positive. So I'm going to go right into applications of applying this to the North Atlantic variability. So I'm going to look at monthly mean SST over the North Atlantic, and what I mean by North Atlantic is 0 to 60 north. For observations, I'm going to use ERSST V5 from 1969 to 2018, so that's 50 years. There's a slight trend in that, so I'm going to remove a second order polynomial from that data set, and there's no sensitivity to these results to that polynomial order. For simulations, I'm going to use CMIP5's pre-industrial control runs. These are runs which have no interannual variability in atmospheric composition and solar variability and the like. And then for the particular autoregressive model, I'm going to use a second order vector autoregressive model. And the reason I choose second order is that we can do tests to decide whether the models are adequate. And it turns out a first order model, which is equivalent to a limb, is not adequate for this problem. So we have to go to second order. And then I'm including 5 annual harmonics, which is all possible harmonics up to the Nyquist frequency. It turns out, I showed you this maximum likelihood or this likelihood ratio test, but it turns out there's a well-known bias in that statistic. And there's also a well-known bias correction. And so I just wanted to mention that I've done that. And then For the dimension reduction, I'm going to use 4 Laplacians over the North Atlantic, and I'll explain that in a minute. But in particular, I'm not using UFs, which is normally what most people use. So Laplacian eigenfunctions are just an orthogonal set of patterns that are that depend only on the geometry of my domain. You're certainly familiar with other kinds of Laplacian eigenfunctions. For instance, Fourier series are examples of Laplacian eigenfunctions. Spherical harmonics are also examples. And here what we're doing is just defining them over the Atlantic basin. And an attractive feature of this is that the first one is a spatially uniform pattern, so that if I project data onto that pattern, that becomes the AMV index. So our first pattern is automatically an index of interest. Then the second pattern is orthogonal to the first, and you can see it's a dipole, which is essentially measuring the north-south temperature gradient. And then the Laplacian 3 is the east-west gradient, and so forth. As you go on to higher Laplacians, you get at smaller and smaller scale. The next question is, how many Laplacians should we choose? And for that, normally you would choose a model selection criteria, but usually those are designed to maximize skill, prediction skill. And here we're not actually interested in predicting, we're interested in comparing variability. So the only test we really, or the main test we need to make sure of is adequacy. And it turns out if I choose 4 Laplacians, that's enough for the model to be adequate. And then the idea I'm having here about why I choose 4 and not more is we often say that models, when you compare models to observations, they're less trustworthy on small scales. So I'm purposely choosing patterns that emphasize the largest possible scales. And if there's a discrepancy on that scale, that would presumably mean that on smaller scales, there would be even more discrepancies. So here's what the AMB index looks like if you don't remove the annual cycle. The top black curve is from ERSST, and then all the other, these are all the CMIP5 models. And actually there are 2 curves which you might not be able to see on your monitor. There's a thick curve which gives the annual cycle and a thin curve which gives the actual value. And you can see, you can hardly tell the difference between those two. And this percentage here next to each of the models is the percent of variance explained by the annual cycle. And you can see all of those numbers are 98% or more. So the vast majority of the variability in the North Atlantic is in the annual cycle, and all the decadal variability that we're talking about, that people talk about, is about 2% of the variability. So this is what the deviance looks like for all the models. So what I'm doing is I'm comparing ERSST before 1993 to model simulations. And the deviance, so the larger the deviance, the bigger the difference between AR models. And this gray line here is the significance level. So any points that are below that show insignificant differences between from the observational data. And you see there's only one dot here, and that's actually observations from the later period. So what I did is I took observations before 1993, and I've included in here observations after 1993. And you see that there's no significant difference for the stochastic process between those 2 periods. But for all the other models, you see there's a very large and significant difference between observations and all the other models. Now, what is the source of this difference? And one hypothesis that's sort of bandied around is that the models have a common bias. So one way we could address that or investigate that is to, instead of comparing models to observations, we compare models to other models and see if they have a common error or not. So that's what I'm going to do here. And if you compute this deviance between every possible pair, you can summarize that in a matrix. That's what I'm showing here. The x-axis is showing the models for the first half of the time series, and then the y-axis is showing the result for models the second half. So what I've done is I've taken, for each model, I have 2 time series, and I split it up into 2, and I'm comparing every first half to every second half. And you probably can't see the numbers here, but that's okay. I've shaded it so that dark gray or just gray means that there's a significant difference. And then where a white space or no shading means there's no significant difference. And of course, you see immediately that the values along the diagonal are white. And what that means is that when I take a time series from the model and a time series from the same model, those tend to be insignificant differences. So this is validating this measure of a deviance, is that it's able to say that if you take a time series, two time series from the same model, you can't find a significant difference. But then for all other cases you find, or almost all other cases you find, there is a significant difference. There are some exceptions. You see that there are these blocks. And if you look closely, these 3 blocks correspond to the 3 Hadjim models. This 3x3 block here corresponds to the 3 MPI models. So what this is saying is that if the time series comes from a model from the same institution, right? If you have 2 models from the same institution, then those tend to be insignificant differences. And another block here corresponds to 2 NCAR models. This block here is the 2 MyRock models, and then this block here is the 2 GIST models. So again, when time series come from models from the same institution, this method cannot find a significant difference. This is another way to kind of summarize the difference. This is called a dendrogram. It's a standard method for finding clusters in data. I don't really have time to go over in detail, but basically the x-axis is my deviance measure. So the more to the right, the bigger the difference. And then the leaf here, this vertical leaf, it shows the maximum deviance among all the members of that cluster. And I've color coded the models so that if 2 time series come from the same model, they have the same color. And what you see is that almost 100% accuracy in pairing one model time series with the time series from the same model. There's a few exceptions. Here, Hadjim 2 CC was paired with Hadjim 2 ES. So again, that's this issue that 2 models from the same institution are hard to distinguish. And here's the observations in black, and they're clustered together and they're by themselves. And then the next best model turns out to be Hadjim. And then the next set of models that are close to it are the NCAR models, and then so forth. So again, this doesn't tell you where the discrepancy is, it just says there is a discrepancy. But the nice thing about this deviance measure is you can decompose it into separate terms. And so we can decompose it to measure differences in the noise covariance matrix, differences in those A matrices, which effectively correspond to our dynamics. So if you were to derive those A's from physics, they would have the Crosby waves, gravity waves, and other things, so dynamics. And then the parameters associated with the annual cycle are given in this last deviance. And so this is what the deviance looks like compared to the observational period. And for each model, there are 3 bars. The blue is the noise difference, the green is the AR difference, and then the red is the annual cycle difference, or the difference in annual cycle parameters. And just scanning across, you can see the biggest bars here are the red, which means the biggest source of difference for all the models is the annual cycle. And what I've marked here in black are the cases where bars are insignificant, and you see only 2 models become insignificant when you consider only the noise in the AR part, so ignoring the annual cycle. And those 2 models are the Hadjim model and the GFDL. So there's 2 models that appear to have consistent variability compared to observations, but still those models have a strong discrepancies in their annual cycle. And then if you compute this, compare the deviance for every possible pair for the annual cycle, you get almost the same result as we found before, confirming the result that not only do the models have annual cycles that differ from observations, but their annual cycles differ from all the other models, unless they come from the same institution. So then what are the features of the annual cycle that dominate this? That's kind of a hard question to answer. If you just look at the difference, remember it's in multi-dimensions. So we have 4 Laplacians that we're looking at. Annual cycle is 12 months, so that's 48 different maps. How do you compare those? And there may be features that catch your eye, but they may not be the ones that the deviance is actually measuring. And so all those differences could be summarized with this delta, and actually I just realized these should be minus signs, not equals. So we're looking at differences of these parameters, and the goal is, can we somehow characterize where the biggest source of these differences are? So it takes quite a bit of ingenious mathematics, but you can show that this deviance for this annual cycle could be written in this form, following this phi matrix. that depends on this, this delta hat, which is the difference in parameters. And therefore, if you perform an SVD on that, you'll decompose the deviance into orthogonal components, and then you can order them by their contribution to the deviance. So this is a way of further decomposing each of the deviances into components that you can show are effectively the same as finding a linear combination of variables that maximizes the deviance. So this is how the decomposition looks like. Here I'm looking at decomposed deviance. So again, the larger the value, the bigger the difference between the two models. This black horizontal line is showing the significance level. So any points that are below that are insignificant, but but this is only for the largest eigenvalue. The significance level pertains only to the largest. And you see all the models except for observations are large. But also what you see is for this first model, there's a large separation between the first and the second. So that is saying that there's one component in this model. This is the NOR ESM model. There's one component that really dominates the error in the annual cycle. And so we would really like to look at that. So that's a natural byproduct of this SV analysis. So once you do this, you can decompose those differences into a time series and into a spatial pattern, into an amplitude. And I just showed you the amplitude, but now we can look at the time series and spatial pattern. So this decomposition looks a lot like a EOF analysis or principal component analysis, but instead of maximizing variance, we're maximizing deviance. So this is what the largest deviance looks like for this model NOR ESM. And you see it tends to have its largest amplitudes around the Gulf Stream. And the black curve is showing the observed value of this for this pattern, and then the red is showing the model. And what you can see is what this is saying is that the models are underestimating the amplitude of this pattern relative to observations. And if you look at another model, a very similar picture is that there is a warming pattern over the Gulf Stream, and then the models tend to underestimate the annual cycle of that pattern. So I think that's all I have time to go over. So just in summary, I've introduced an objective method for comparing annual cycle and internal variability between models and observations. And a very key part is we really worked hard to derive a test where there's a significance test, so we can actually say if the differences are significant or not. And then each of these deviance measures can be decomposed into an orthogonal set of components ordered so that the first maximizes the difference. And I'm hopeful that this could be insightful in terms of identifying where the largest sources are, where if you're trying to improve the model, where you might want to concentrate your efforts. We've applied this to monthly mean North Atlantic SST, and we find that each of the CMIP5 simulations differ significantly from observations, and they differ from each other. So there's no sort of common error between the models unless they come from the same center. And most of this difference is dominated by having an incorrect annual cycle. And then when you perform this decomposition, we find that when there's a dominant factor, it tends to be this pattern where it underestimates the winter to summer change in the subpolar or Gulf Stream regions. So with that, oh, actually, if I have one more minute, I mentioned that there's these decomposition methods. And if you haven't sort of seen how this works, there's a new book out, or relatively new book, that describes these. So hopefully you don't mind this shameless promotion of my book, but I'll just stop here and I'm happy to take questions.
All right, thank you so much, Dr. Dersol, for that great presentation. We're gonna get that book, so thanks for that promo. All right, I'm gonna open up the floor now for questions. So remember, you can raise your hand using the raise your hand feature. If not, you can type your questions in the questions box, and I'll read it out loud for Tim to answer. I'm not seeing any, so I'm gonna go ahead and ask one. Do you have any future work related to this research?
Sure. So in effect, the method only works for stationary time series, except for this annual cycle. So the annual cycle is our first effort to go into the non-stationary realm. But of course, global warming is a key area. So we're working on what's the natural generalization to this to handle global warming. I have other things that I have in mind, but that's as far as I want to go right now.
Perfect. Do we have any questions from the audience? I encourage everyone to ask. All right, we have one from Nicholas Schneider. Let me unmute you. Let's see if that works. So I'm trying to unmute Nicholas. Let me. So I'm trying to unmute. Okay, go ahead. Now you're green.
Okay,
yeah, it's working.
good.
Go ahead.
It wasn't obvious to me that this button is working. Okay. So thank you very much for the talk. Very nice. I just wonder, can you detect or do you see any coupling in terms of, or any suggestion that if the annual cycle is bad, then the interannual or the dynamics that you call, that they are also bad? So that there's a coupling between these two sets that you separate here.
Yeah, so I would say I don't think I can detect that. That's a good question. I'm thinking right now, I don't think I can actually detect that. If I were to detect that, I think that's assuming that the variability would depend on the annual cycle. That would introduce or push me into the realm of cyclostationary statistics. And I think at the way I formulated, I'd have to do another generalization. So I can't, this model cannot detect those kind of couplings that you're talking about.
All right, we do have another question we have two, from Thomas Knudsen. What will be the application to multi-decadal variability of your project?
Yeah, so as long as the autoregressive model can capture the decadal variability, then I believe that this method could be used to compare decadal variability. So I have applied it to annual means instead of monthly means. Look at annual means. And that's what a lot of people use when they're looking at decadal variability. So I've published in that. So I think as long as the model is adequate. So there is a tricky question about whether it's adequate. So sometimes when you look at certain features in the ocean, their autocorrelation function, they don't quite fit an AR model. So sometimes they drop down very quickly and then linger away from zero after a while. And so that would not be well fit by this type of model. So I would be concerned about drawing conclusions if that kind of feature is in the data. But if it's sort of decays like a power law, like an AR model, then I think this method should work for decadal variability.
And he has a follow-up. The initial plot with two models versus observations seemed to show a difference between show a difference in AMO-like multi-decadal variability, but maybe not significant.
Yeah, you're saying, I think I'm going to guess what you're saying is that this, you might say, looks like a stronger low frequency variability than what is seen here. Yeah, so what I can say just two things about that. One is within this test is a test of internal variability. So you remove the annual cycle. And when you do that, it turns out that both those time series, these are the ones I showed from HADGEM and GFDL, according to this test, they're consistent. Now, whether to really be sure, what I would want to look at is the autocorrelation function for each of those and compare to observations. And I actually have not done that. So that's a good point, good question.
All right, so hopefully that answers both of Thomas's questions. All right, I don't see any more questions. So at this time, I will thank Dr. Del Sol for that great presentation. And now we're gonna move on to our next presenter of the day, Dr. Dennis Volkov. He is an oceanographer at the University of Miami and at NOAA's Atlantic Oceanographic and Meteorological Laboratory, where he has worked since 2013. His current research interests include different aspects of ocean dynamics, with a particular emphasis on regional sea level and ocean circulation changes. At this time, I will turn over to controls to you. Thank you so much, Dr. Volkov, for being here with us today.
Good afternoon, everybody. Just let me start my. You see my presentation, right?
Yep.
Okay. Okay, good afternoon, everybody, and thanks for attending this seminar. So today I'm going to discuss how the Atlantic meridional Newtonian circulation is related to sea level and how it influences coastal inundation along the United States East Coast. So sea level rise is among the most challenging consequences of global warming, especially for coastal communities. And while the global mean sea level has been rising due to the melting of glaciers and ocean warming, we see that ocean and atmosphere dynamics make sea level changes spatially and temporally non-uniform, as demonstrated by these regional sea level trends. And the regional sea level variations that are not directly related to ice loss or net heat absorbed by the ocean are usually termed dynamic sea level changes. In fact, the ocean exhibits certain patterns of dynamic sea level change with alternating signs over different time intervals. And together with the global mean sea level rise, these dynamic patterns provide background conditions for high frequency, large amplitude, weather-driven sea level fluctuations that actually cause coastal inundation, and especially when they're superimposed on spring tides. So therefore, it's in order to improve sea level projections and predictability of floods, it's important to understand the mechanisms of this regional dynamic sea level variability. Okay, so low-lying coastal regions, including areas along the United States East Coast and also the Gulf of Mexico, are the most vulnerable, among the most vulnerable to sea level rise. And actually, the US East Coast has already been identified as a hotspot for accelerated sea level rise in the North Atlantic. There have been plenty of studies exploring different processes that could be responsible for the regional acceleration and also spatial variation of sea level rise. And among these processes are longshore wind forcing, atmospheric pressure loading, weakening of the Gulf Stream, warming of the Gulf Stream, also vertical land motions, and slowdown of the Atlantic meridional Newtonian circulation. The impact of the Atlantic meridional Newtonian circulation, or the AMOC, is of particular interest because some state-of-the-art climate models project a decline in the AMOC towards the end of this century in response to anthropogenic forcing. And this decline will be accompanied by accelerated sea level rise along the western boundary. The century-long AMOC proxy data, based primarily on upper ocean temperature, indicates that the AMOC is already slowing down. However, direct measurements of the AMOC are still too short to confirm this with certainty, and this observational data still mainly reflects interannual variations. So how is the AMOC related to coastal level, sea level? Well, first of all, there is a direct mechanism that is due to the geostrophic balance. The potential decline in the AMOC will be accompanied by dynamic sea level rise along the western boundary of the North Atlantic, and this could dramatically increase the flood risk. But then second, there is also an indirect mechanism, which is actually the focus of this presentation. And according to this mechanism, the AMOC changes lead to gyre-scale heat convergence or divergence, which in turn affect coastal sea level changes and therefore the frequency of floods. So the objective of this research was to establish the relationship between the AMOC and the Gaia scale ocean heat convergence in the subtropical North Atlantic, and also the frequency of floods along the United States East Coast. So satellite altimetry observations over the last 30 years almost have shown that the interannual to decadal dynamic sea level variability in the North Atlantic is characterized by large-scale tripole pattern, as you can see in this figure in the left, and it's known as the North Atlantic sea surface height tripole, in which the subtropical ocean gyre varies out of phase with both the subpolar gyre and the tropics. As demonstrated by the first principal component of the low-pass filter at sea surface height anomaly here, or as I call it, the tripole index, the subtropical band of the tripole was characterized by an overall sea level decrease in 1993 to 2010, and then a rapid sea level rise in 2010 to 2015. So we also used the ECHO version 4 ocean state estimate for regional heat budget analysis, which I will talk about shortly. But first, I'd like to demonstrate that the model adequately simulates the variability in the North Atlantic. And here in the right figure, you see the leading EOF of the dynamic low-pass filter at sea surface height in the model, showing that the model reproduces the tripole pattern of the variability reasonably well. And here the black and blue curves show the leading principal components or the tripole indices calculated from altimetry, this is black, and from the ECHO data in blue. It appears that the tripole is mostly determined by the thermostatic sea level variability, and this is evidenced by the EN4 temperature data that we used, and that means that the tripole mainly indicates ocean heat content changes. I'm not showing the spatial pattern of the leading EOF of the thermostatic sea level here because it looks similar to the leading EOF of the altimetry sea level, but the tripole index derived from the thermostatic sea level is shown here by the red curve. The plot in the right bottom corner shows the time depth diagram of the potential temperature averaged over the area shown by this black rectangle in the subtropical North Atlantic. And you can see that the rapid increase of sea level in 2010 to 2015 was associated with a remarkable warming in the subtropical North Atlantic that extended down to at least 2,000 meters depth. So let's now analyze the mechanisms that drive this tripole pattern of the variability. And first of all, we can see that the tripole looks like an imprint of the North Atlantic oscillation. And indeed, it's correlated with the low frequency NIO, as shown by this time series in the lower plot. So the correlation between the tripole index and NIO is 0.7, with the tripole lagging behind the NIO by 9 months. Furthermore, the sea level pressure and 10-meter winds from the ARA5 analysis projected on the tripole index exhibit the familiar NIO dipole pattern, which indicates that strengthening of westerly and trade winds in the subtropical gyre leads to higher sea level in the subtropical gyre and lower sea level in the subpolar gyre, and opposite occurs during the negative NIO phases. Well, of course, correlation does not mean causation, but the relationship with the NIO is expected as the ocean adjusts to atmospheric forcing. So in order to investigate what drives the tripole in more detail, we have performed a regional heat budget analysis in the subtropical North Atlantic using the ECHO model. And I have shown earlier that the model realistically simulates the tripole. For additional model validation, here I am comparing meridional heat transports at 26 north and 41 north on these lines from the model and from available observations. So the model is shown by the blue curve and observations by the red curves. The observed anomalies of the meridional heat transport, or MHT, come from the rapid MOC at WBTS array, which is at 26.5 north, and from the combination of altimetry and Argo data at 41 degrees north. And you see that there is a very good agreement at 26 north and a reasonable agreement at 41 north, which suggests that the model realistically reproduces heat divergence between the two latitudes. In this plot on the right, you can see that the full depth heat budget terms between 26 north and 41 north. The black curve is the time change of the volume integrated ocean heat content between the two latitudes, which is the sum of first heat advection into the region, or simply the difference between the MHT at 26 north and 41 north. This is shown by the red curve. Second, it's the volume integrated forcing term that includes surface heat exchanges and geopotential forcing. This is the blue curve. And finally, the green curve shows the diffusion term. So as these all terms illustrate, the subtropical band of the tripole gains heat due to the meridional oceanic heat convergence. So the advection term is always positive, as you see, and it loses heat to the atmosphere and due to diffusion. What is important to note for the objectives of this study is that the meridional heat transport convergence is the primary driver for the interannual variability of oceanic heat content in the subtropical band of the tripole. The contribution of the forcing term is of secondary importance, and the dissipation term can be, its contribution to the variability is negligible. Also here, the red dotted curve, if you can see it, it shows the observed heat convergence between the two latitudes from the two observational arrays. So next, I'm comparing the meridional heat transport divergence between 26 north and 41 north, shown by color shading. So that indicates warming in pink and cooling in blue. And also I'm comparing it with time derivative of the tripole index, shown by the black curve. So the two time series match together quite well, meaning that the subtropical band of the tripole is mostly driven by heat divergence. I should also note that this heat divergence is induced primarily by the AMOC because the meridional heat transport at the two latitudes is mainly due to the overturning and not due to the horizontal gyre circulation. So you may wonder how important the tripole-related variability is for coastal sea level changes. And to address this question, I'm showing here the portion of an interannual dynamic sea surface height variance explained by the tripole locally. And you can see that the tripole is responsible for up to 80% of the variability in the subpolar North Atlantic, in some interior parts of the subtropical gyre. But what is particularly important for objectives of this study is that it explains from 60 to 80% of the local interannual sea surface height variance south of Cape Hatteras along the US coast, along the Gulf Coast, and also in the Western Caribbean. In the right figure, the colored circles here show the locations of tide gauges that we used for this study. There were 44 tide gauges. And the color indicates the amplitudes of the tripole-related sea surface height changes at tide gauges, obtained by regressing the tide gauge records on the tripole index. And what you can see is that while north of Cape Hatteras, these tide gauges, north of Cape Hatteras, the tripole-related changes are small and negligible. On the other hand, south of Cape Hatteras, the amplitudes of the tripole-related sea level changes range between 5 and 10 centimeters. And just to illustrate that these amplitudes are relatively large, I'm also showing in this insert figure, I'm showing the global mean sea level by the black curve here. And the time series show the tripole-related sea level change at several tide gauges to the north and to the south of Cape Hatteras. And you see that the tripole-related changes south of Cape Hatteras are comparable actually to the magnitude of the global mean sea level rise during the last 30 years. So that suggests that the impact of the tripole on the frequency of coastal inundations is equal or sometimes even greater than the impact of the global mean sea level rise. Okay, so here I'm showing the probability density functions for daily highest water levels, and that's relative to the mean high water tidal datum. And that's at 4 characteristic tide gauges to the north of Cape Hatteras. This is Boston and Atlantic City, shown here. And south of Cape Hatteras, this is Virginia Key in Miami, and also Galveston Key in Texas. So these PDFs are for the time period from, so they are calculated over 5-year time intervals. And what you can see here that due to the global mean sea level rise, the mean values of these quasi-Gaussian distributions have been shifting towards higher water levels, thus increasing the probability of water levels breaking the minor flood thresholds shown here by the orange vertical lines. What is interesting to note is that south of Cape Hatteras, the probability density functions for the years of 2015 and to 2019, that's shown by the red curves, clearly stand out as exhibiting the largest shift relative to the previous 2010 to 2014 time period. And I will show shortly that this change is largely due to the impact of the giant scale dynamic sea level variability described by the tripole. So in order to demonstrate the impact of the tripole on coastal inundations, I'm showing here the annual expected exceedances for daily highest water levels in 2015 to 2019 at several tide gauges along the United States East Coast. So these tide gauges are shown here by our red circles. And it's for 3 scenarios. So the first one shown by the black curves here is the actual scenario. Basically, it's what's going on in reality. Then the scenario when the global mean sea level rise has been subtracted is shown by blue curves. And finally, the scenario when the tripole-related sea level changes have been removed is shown by the red curves. So the y-axis, note that the y-axis here in these plots shows the number of days per year when water level exceeds the value shown along the x-axis. So the expected exceedances demonstrate that if the global mean sea level rise were removed from tide gauge records, there would be about a 2-fold or greater decrease in the annual number of flood days at almost all locations along the coast. If the tripole-related sea surface height changes were removed from tide gauge records, then the annual number of flood days to the north of Cape Hatteras would not change significantly, which means that the impact of the tripole on the frequency of floods here is small or negligible. On the other hand, the removal of the tripole from tide gauge records to the south of Cape Hatteras would reduce the annual number of flood days by about 30 to 50%. And the impacts of the tripole and so from these plots, we can see that the impacts of the tripole and the global mean sea level rise on the frequency of floods along the US southeast coast or south of Cape Hatteras and also in the Gulf of Mexico in recent years have been comparable. And finally, to summarize, in the top diagram, I'm showing the actual number of flood days per year. And in the lower diagram is the difference between the actual number of flood days and the number of flood days that would happen if we subtracted, if there was no tripole. So you see that due to global mean sea level rise, the number of flood days along the US northeast coast has been increasing and reaching a maximum in 2018. On the other hand, the frequency of floods south of Cape Hatteras, including the Gulf Coast, was rather low and stable until about 2015, and then it started to increase substantially. And that south of Cape Hatteras, actually, the number of flood days due to the tripole, if the tripole was removed from sea level tide gauge records, then the number of floods would be decreased by 30 to 50%. Also, what is interesting to note is because the tripole was characterized by sea surface height decrease in the subtropical gyre in 1995 to 2010, it was reducing the number of floods during this period, which is reflected in this by this blue shading. And this apparently compensated for the impact of the global mean sea level rise, and that explains why south of Cape Hatteras, the number of floods prior to 2015 was rather low and stable. So I'm ending here. So this is my summary and conclusions. I'm just leaving this this slide on, and I thank you for your attention and welcome your questions.
I'm gonna presentation for questions, and we do have one. It actually came in during your presentation from seniors. Am I seeing the North Atlantic? Asks in slide 4, Atlantic SSH tripole suppressed the U.S. East Coast sea level for a certain period.
Excuse me, I didn't hear everything what you said because of the connection problem. I heard about slide 4, right?
Oh, can you hear me now?
Yes, I can, but every other.
Yeah, so slide 4, am I seeing the North Atlantic SS? Can you hear me?
Yeah.
Can you hear me now? Okay, so the question is, slide 4, the North Atlantic SSH tripole suppressed the US East Coast sea level for a certain period?
You mean this slide?
The slide 4. That's what the person is asking.
Okay. So yes, it can, as I showed actually in the last slide. So the tripole was characterized by overall lowering of sea level in the subtropical gyre prior to 2010. So during this time interval, yeah, it was suppressing actually the effect of the global mean sea level rise south of Cape Hatteras. But then after 2010,
all right,
increase, and that actually the tripole was responsible for the accelerated sea level rise. And in fact, it has been shown, for example, that accelerated sea level rise along Florida East Coast was 5 times greater than the global average in from 2010 to 2015. And that was mainly due to the warming of the Florida current, the Gulf Stream. But that's not just locally, but it was also related to gyre scale warming in the subtropical gyre of the North Atlantic, and that's related to the tripole node of the variability. Did I answer?
Thank you. Yeah, so the person said thank you. So I guess that answered the question. We do have another question from Sister Wilfels. Does the Tripole SL pattern reflect a Sverdrup balance with the wind curl?
Yeah, so I would say that because there is a relationship with the NAO also, so it's a it is related to wind forcing.
All right. Do we have any more questions? We do have time if the audience have more questions for Dr. Volkov. I am not seeing any other questions. So with that, thank you so much, Dr. Volkov, for that great presentation once again. And I would like to thank everybody for joining us. This set of presentations for our series on the Decadal climate variability and predictability studies. I would like to thank today's presenters, Dr. Del Sol and Dr. Volkov, for taking the time to share their work with us. The recording of today's webinar will be available within the next week on our website, cpo.noaa.gov/cvp. We hope that you will join us for the next webinar, which is next Thursday, June 1st. Let me pull up the presenters. Give me 1 minute right here. And show my screen now. All right, all right, so you're seeing the next week's presenters, Wheel from the University of California, Santa Cruz, mechanisms of interannual to decadal scale predictability for ocean physics and biogeochemistry in the California current system, and Samuel Morgan from the University of Colorado Boulder, predicting marine stressors multiple months in advance. So with that, we'll see you next Thursday. Have a nice long weekend, and yeah, see you next week.
Thank you. Bye.